Alright, Assalamualaikum and good day everyone. So in this video, I'm going to cover lecture 8, and we are going to learn how to solve second ODE, that is non-homogeneous. Okay, so we are going to cover two different methods. The first one is undetermined coefficients, and the second one is variation of parameters. So let's do a quick recap on the types of ODE that we have. Previously in lecture 6 and 7, we have learned how to solve second ODE, that is linear and homogeneous. So in this lecture, we are covering non-homogeneous, whereby the right side here is not 0 anymore, but there is a function. Okay, so to solve non-homogeneous ODE, we need to solve the homo part and the non-homo part separately. So if this is an ODE, so the left-hand side here, the purple colored equation is the homogeneous part. So we have to find the general solution, which is equal to AY1 plus BY2. To get this value, we have to use either constant coefficient method or Euler-Cauchy method. This has been covered in the previous lecture. So if you still don't know how to find the general solution for homogeneous ODE, please go back to the recorded lecture first before you continue watching this video. All right. So since now we have to do the solution separately for the left-hand side and for the right side. Now we will have two different y. From now on, for the homogeneous solution, we will call it YH, which stands for Y homogeneous. And for the right side, for non-homogeneous part, the y we will call it as Y particular or YP. To find YP, we are going to use either two methods, which are undetermined coefficient or variation of parameters. After we get the function of YH and YP, we will add them together, and this summation of YH and YP is the final solution of a linear non-homogeneous second ODE. Just for you to know, this equation is also based on superposition principle that I have covered before. Okay, so linear non-homogeneous second ODE can be solved using undetermined coefficient and variation of parameters. So for the first method, it involves guessing a solution, then determining the coefficient. Guessing the solution means we are guessing the YP, and then we are going to determine the unknown coefficient. So since we are determining the coefficient, that is why this method is called undetermined coefficient. The second method is a method that involves varying the parameters in the general solution to find the non-homo solution. So at this stage, the description or the meaning of these methods doesn't make sense yet, but later you will understand why what is the method. So for the first method, it's the pro and cons of this method is it's easy, simple, and direct because it doesn't it has less complex derivation and no integration at all. But it has limited applicability, means that not all types of ODE, non-homogeneous ODE, can be solved using this method. And the second one is, since this method involves guessing a YP, if we guess the wrong YP, then the answer will be also wrong. Okay, for the variation of parameters, the good thing about it is it's applicable to all non-homogeneous ODE, and it is also systematic. whereby we go step by step, and we don't need to guess the solution, but the calculation will be a little bit complex because it involves integration. And the second cons is the ODE that we are solving must be in standard form. If we forget to convert it into standard form, then the answer will be wrong. So I will not be covering the theory because I want to simplify the lecture. So if you want to know more about the theory of both methods, you can go to the link that I've given here. First, let's go to the first method, undetermined coefficient. I'm going to show you through example so you can see the steps. All right. So the question is, solve y double prime plus 4y prime minus 2y equal to 2x squared minus 3x plus 6. You notice here that the right-hand side is no longer 0 as in the previous lecture. Now we have a function of Rx in the right-hand side. Okay, then how to solve this ODE? The first step is to find YH, the simplest one and easiest part because we have done it in the previous lecture. I'm not going to cover on how to find YH here. So please, if you don't know how to find YH, please watch the previous recorded lecture. So I'm just going to give you the value of YH here, which is this. This is this solution. And the next step after finding YH is we have to find YP. So to find YP, first we have to guessing or assume the function of YP. So we have to assume by looking at the types of function of Rx here. So since this Rx is a polynomial function, it's a quadratic equation, but it's a polynomial. In more generally, it's a polynomial function. So if we have a polynomial function, then the assumption of YP or the guess of YP should also be a polynomial function. But we have to change the constant 2, -3, and 6 here into unknown constants of A, B, and C. Get it? So if you have a polynomial here, then the assumption is also polynomial, all right? At the equal power of x. So if you have x squared here, your assumptions should be also x squared, starting from x squared. Now, we have to find yp prime and yp double prime because later we want to substitute all of this back into our ODE here. So this is the ODE, and we substitute the yp prime and yp double prime into the left-hand side. So we will get this particular equation. And this part is actually equal to the right-hand side, the non-homogeneous part of the ODE. So after rearranging, then we will get, rearranging means that we are grouping the terms. For x squared, we group the constant, and we also group the constants for x, and we also group the constants for x power of 0, which is here, there is an invisible x power of 0, which equals to 1. And after that, we can see that this equation is comparable. Means at the left side, there is x squared, x, and x power of 0. And the coefficients here are comparable or equal. So if you take -2a and equal to 2, you can find what is the value of a. So for the blue equation, you can compare the value, and you can find the value of b. And for the purple equation, you can find the value of c. After getting the value of a, b, and c, then you substitute it into yp. So remember the YP, the previous YP is ax squared plus bx plus c. Just substitute the value of a, so we get this solution. After getting YP, our last step is to add YH and YP. Just add it simply. And for your information, the YH will be in terms of unknowns, A and B. But for the Y particular, it will be, there will be no unknown terms here. So this is the general solution of our ODE here, right? Okay, let's go through in more detail about this method. And I've said before that one of the cons of undetermined coefficient method is it has limited applicability, meaning that it can only solve certain types of Rx. So what are the Rx that can be solved? So let's focus on these three types of function. So the first one is polynomial, second one exponential, and lastly sine or cosine. So any Rx that are sum of the above and products of the above are also can be solved using this method. Okay. Polynomial Rx function examples are these examples. Just want to highlight here that a constant 2 is also a polynomial, but there is an invisible x power of 0 over here. And this is also a polynomial function, x cubed, but all the coefficient for x2 and x power of 0 is 0 here. So we have only x power of 3. The second type of function that can be solved is exponential, such as exponent 2x and this exponent function. The third one is sine or cosine function. Just want to highlight at this point that tangent function cannot be solved using undetermined coefficient method, only sine and cosine. So any sum of the above or products of the above can also be solved, right? Now, previously in the previous example, we have done something similar like this one, all right? We have to find the YP. So for this polynomial, which is 2x squared minus 3x plus 6, the YP is the same equation, but we just have to change the value of 2 into A, negative 3 to B, and 6 to C. Basically, all the numbers change to unknowns, okay? Similarly for this equation, but let's look at x power of 3 here, x cubed. So if we have x cubed, even if there is no terms after x cubed, there is no 2 power of x squared. In Y assumption, you have to include all terms, all right? Have to include x power of 2, x power of 1, and x power of 0 for the YP, okay? For exponential, for the first one example is exponent 2x. There is a constant of 1 here that's invisible. So just substitute that 1 constant into A, and the 2x here remains constant, okay? Similarly, for this, the second example, the 8, the number here changed to A. All right. Special case for sine and cosine function. Okay, let's see. Let's see here for 2 sine 2x. If the function is either sine or cosine, then the YP must include both terms, cosine and sine. Okay, change the 2 into constant, which is A and B, but the sine here, where for the YP for the sine will be both cos 2x plus B sine x, sine 2x, okay? Similarly, or if the function already have cos and sine, then you don't have to duplicate it. But for the third case here, if you can see that the cost value here is different with this. So for this case, it's cos 2x, and for this case is sine 5x. For the second example, the value here are the same, 3x and 3x. So the assumption is this only one assumption. But for this one, we have two different value of cos and sine. So meaning this is separate function, function 1 and function 2. So we will have a separate yp for 2x. So a cos 2x plus b sine 2x, and another yp for sine 5x. So we just add up here plus c cos 5x plus d sine 5x. All right. Okay, and you can see later for yourself for some of the above functions and products of the functions. Now let's do a simple exercise to guess the right YP for these functions. If you want to do the exercise on your own, please first pause this video, do it, and continue watching, okay? Okay, so this is the answer for the YP of the given function. So similarly as I have explained before, just want to highlight for x power of 4, you have to mention for x power of 3, x power of 2, x power of 1, and x power of 0 as well, even that there is no terms afterwards, all right? And yeah, everything I have explained before. So let's go to the next part. Now, so even if this method is very simple, because it involves guessing, right? But there is a glitch in the method, meaning that we have to modify this the assumption so that it will be correct. Sometimes our guess is not correct. For example, for this case, solve y double prime minus 5 1 prime plus 4y equal to 8 exponent x. So the first step, as we have done previously, to find the YH is this equation, and YP is a exponent EX. We just simply change the 8 value into unknown A. And then we have to check here. The YP term, the YP, which is which is exponent X, is the same as one of the terms in YH. So let's see here, exponent X and exponent X. So just to want to highlight, e power of 4x is not the same as e power of x because there is a 4 here. But this is the same, e power of x and e power of x. So let's see, let's prove why this cannot be a solution. So when we do yp prime, yp double prime, and substitute into the ODE, later the left-hand side will equal to 0. When it's equal to 0, then we cannot find the A, right? If we cannot find the A, means that our assumption is wrong, all right? So how to twist the assumption? So if the guess YP solution, guess YP is a solution in one of the terms of YH, then it has to be, YP here must be modified by multiplying with X, or if it's still the same with YH, multiply with X squared. If it's still the same with YH, multiply again with X power of 3. So for this case, we have to, we only have to multiply with X. So our new YP is AX e power of x. Now the term is not here, so it's there is no similar terms in YH. Okay, let's do an example first. So y double prime minus y prime plus y equal to 2 sine 3x. First step is to find the YH. This is the equation for YH. And we have to find YP. The first step to find YP is to do assumption or guessing. Guessing based on the type of function in Rx. This is a sine function. Remember, if we have sine function, then the assumption of YP is both sine and cosine. So the YP is here is A cos 3x plus B sine 3x. Okay, both terms are included, cos and sine. Now, to make sure that this equation, this assumption is correct, we have to check if any terms here is equal to YH. Is there any equal terms? Cos here is same, but the value in front of x is different. For this part, for YH is square root 3 over 2, but for YP it's 3. So YP in this case is not equal to YH, meaning that it can be a solution. Alright, so find YP prime and YP double prime, and later we substitute into the ODE here. This is the left hand side. Substitute the YP inside the ODE, and that part is equal to the non-homogeneous part, which is 2 sine 3x. We rearrange it, we group the terms for cos x and 3 sine 3x. After rearranging, I've added a new term here, which is 0 cos 3x, because actually there is an invisible cos x cos function here, but there is a 0, but the coefficient is 0. That's why it appears 0. Okay, we do this so that we can compare the coefficient in front of cos 3x over here to 0. All right. So negative 8a minus 3b equal to 0 is our first equation. From this, we can find the value, the equation of a, and from this part, from the sine 3x coefficient, we can get 3a minus 8b equal to 2. Substituting, and finally, we will get a and b. Okay, just if you have done this differently, meaning that you solve W equation first, finding the A, and then you solve the red equation, then you will get a different value of A and B. So don't worry, these values of A and B are also correct. So if you accidentally saw your friend's answer during final exam, please do not panic, because most probably both of your answers are correct. So either A or B values that you get, just substitute into the YP and add YP and YH together, and you will get the Y value. I mean the solution of the ODE. All right. Let's go through another example, which is y double prime minus 5y prime plus 4y equal to 8 exponent x. For this case, our right-hand side is a exponential function. First step, find YH. So this is the YH I give you here, so you didn't have to do it. And so the first one, the second thing to do is find YP. To find YP, we have to guess and YP. Since this is an exponential function, then the YP is also exponential, but we change 8 into an unknown constant A. Now we have to check if YP is equal to any terms in YH. So in this case, you can see that exponent x is present here. Okay, So means that there is equal term and this cannot be a solution for this particular ODE, even if this should be our particular solution. So we have to modify this so that it is not equal to YH multiplied by X. So we get AX exponent X. After, now we have to check again if there is any terms. Sometimes if you have an equal root, remember this, there will be an X here. Okay, BX exponent for X if this ODE left hand side is equal root. So if there is also still an X here, YP, the second YP that you get is still not a solution. So you have to multiply again with X. So your YP will be AX squared exponent X. But for this case, since this one, since the ODE is distinct, equal and distinct, then this is the YH. The YH doesn't have any X after the B term. So your YP in this case is AX exponential X. Find YP prime and YP double prime. And then we can substitute into the ODE. And then we get the, after comparing, we will get the value of A. After getting the value of A, substitute it into the YP and add YH that you obtained initially and the YP that you get here. And finally, you will get the general solution of the non-homogeneous linear second ODE in the question. Okay, I hope you understand. Okay, let's now we have covered undetermined coefficient method. Now let's learn how to solve variation of parameters method. So just for you to note that VP steps or variation of parameter steps in first ODE that you learned with Dr. Shakina in lecture 4 is not equal to second ODE in this lecture. The steps are different. So you have to pay attention. And if you forgot how to solve VP in first ODE, then it doesn't matter. And I just want to recap based on the concept of matrix and the concept of determinant. So for the matrix of A, 2 by 2 matrix given by A, B, C, D, the determinant of matrix A is AD minus B times C. So, for example, if we have a matrix of C over here, so the determinant of C is 4 times 8 minus 6 times 3. So please remember, please recall this formula and remember because we have to use this later in solving the second ODE. I also want to recap in solving the second ODE homogeneous equation that we have covered in the previous lecture. The general solution is y equal to ay1 plus by2. All right, so in this method, we are going to use y1 and y2 from the general solution of the left-hand side, which is the homogeneous one. Okay, so as I have said before, to find a solution for a non-homogeneous linear second ODE, we have to find YH and YP separately, right? So for YH, we can use the constant coefficient and Euler-Cauchy methods. And for YP, we can use undetermined coefficient that I have previously explained, or we can use variation of parameters. So to find YP using the second method, there is a formula. So instead of guessing, as in the previous method, we are going to use this formula. This formula consists of U1 Y1 plus U2 Y2. y1 here and y2 here comes from the previous general solution of the homogeneous part. Okay, so basically we already know what is y1 and y2 from the homogeneous part. Now we have to find u1 and u2 to find the yp. Okay, let's see an example first. Solve y double prime minus 4y prime plus 4y equal to x plus 1 exponent 2x. So the YH here is a exponent to x plus bx exponent to x. And now the second step, we have to find yp. And the equation for yp is u1 y1 plus u2 y2. But the step to find yp first is to find the Wronskian determinant w of y1 and y2. Wronskian is W is a matrix form of y1, y1 prime, y2, y2 prime. So you have to find the determinant of this matrix. First, you have to find the y1. y1 you can easily get it from the homogeneous solution. So y1 is exponent to x, y1 prime. Just differentiate this equation. You will get 2 exponent to x. Y2 comes from, again, this part of the y homogeneous. And y2 prime is 2x exponent to x plus exponent to x. So just substitute the values into the matrix, and you can find the determinant of W using this formula AD minus BC. So this term times with this term minus with x exponent to x times with 2 exponent to x. Later, after calculating that, you will get this equation exponent for x. After that, we have to find u1 prime and u2 prime. So this is the formula of u1 prime. u1 prime is negative y2 rx over w, and u2 prime is y1 rx over w. Just substitute the value of y2 and rx. Rx means the non-homogeneous part here, which is x plus 1 exponent to x. Substitute it here and substitute the value of w that we have in the previous slide, and you get the u1 prime. Similarly, for u2 prime, instead of y2, we have y1 here, and there is no negative sign in front of the equation. And after substituting, you will get the value of u2 prime. Now, if you realize earlier, our equation of yp is u1 y1 plus u2 y2, not u1 prime, not u2 prime. So we have to integrate u1 prime that we get here and u2 prime that we get here to get u1. So just integrate both equations, and you after getting the u1 and u2, substitute into the equation of yp to get the yp solution. So this final is the solution of the non-homogeneous part of our ODE. To get the general solution of both parts, just add YH and YP together. Okay, now we should go through some of the basic reasoning of the variation of parameters method, the basic of the theory. Okay, so the YP for the variation of parameters is equal to u1 prime u1 y1 plus u2 y2, where the y1 and y2 comes from the homogeneous solution. But the thing wonder here is why this equation is a valid solution for the non-homogeneous part. Why suddenly we think that this is a solution? So just recall back that if we substitute YH, which is the solution of homogeneous, back into the ODE of the solution of the question, the right hand side will be equal to 0, because when we solve an ODE, when solving it, meaning that what we have learned in lecture 6 and 7, when we solve it, we actually found the function that satisfy the ODE when we substitute it back. So when we put YH back into the ODE that we have done, so YH here is AY1 plus BY2, we will get the right hand side will be equal to 0. When we compute these values, we will get 0. Okay, but if we change the unknown constant of A, B here, change it into a function, unknown function, then the right hand side is no longer 0, because we already modified the value, the constant, right? So it will not become 0, it will become a function called Rx. So since substituting yp equal to u1 y1 plus u2 y2 back into the ODE will be equal to Rx, then this is a valid solution to the non-homogeneous solution, non-homogeneous part of the ODE. I know this is very hard to digest. You don't have to understand, but I have to tell you, because if someday you are wondering why the variation of parameters solution works that way, then you refer back to this slide. Now, after getting the YP, knowing that YP is valid, now the next thing to be concerned of is how to find U1 and U2. So from very long substitution and rearranging equations, two equations are obtained. I did not show it here. If you want to know more, you can go to the link that I have provided in this previous slide. But it's important to know that these two equations are obtained. And similar like when you want to find A and B values from 2 or 3 equations, right? We just have to rearrange and substitute everything. Similarly, for this one, we have two equations. Then you can find the U1 prime and U2 prime. So the equation of U1 prime is this equation after rearranging from this, and U2 prime is this equation. It looks a little bit complex, so this equation is simplified by converting the bottom part of the equation into W, whereby W is a Wronskian determinant of Y1 and Y2. Wronskian, the W here is in terms of matrix, whereby the values inside the matrix are y1, y2, y1 prime, and y2 prime. So we have to get u1 prime and u2 prime, we have to find the determinant of w, which can be found by this formula, AD minus BC. After getting the value of w, you can substitute here and you can find the u1 prime and u2 prime. Since the equation of yp is not in terms of prime, it's u1 and u2, you have to integrate u1 and u2 to get you have to integrate u1 prime and u2 prime to get u1 and u2. Okay. And another reminder, for variation of parameter method, the ODE must be in general form, or else your answer will be incorrect. Let's go through example 2 for the second method. Solve for y double prime plus 36y equal to cosec 3x. First step is to find YH. YH now, the first step is for VP is to check if it's in standard form or not. So for this case, please remember what is the meaning of general form. The general form of ODE means that nothing is in front of the y double prime. So now we have 4 in front. So please divide the equation, the ODE, by 4. So you can eliminate the number of 4 here. So 36 divided by 4 is 9. So this part will be equal to 1 over 4 cosec 3x. Now we have to use this second ODE for using the variation of parameters method. To avoid confusion, please cross out this equation so you will not take the wrong Rx later. Now, step 1 is to find YH. YH is given here. Next step is to find YP. For YP, for this method, you have to find the Wronskian determinant of Y1 and Y2. So just substitute the value of Y1, Y1 prime, Y2, Y2 prime. Y prime can be easily get from the general solution here, cos 3x, and Y1 prime, just have to differentiate this Y1, and Y2 can be obtained from the YH, and again, Y2 prime, just differentiate the equation of Y2. Substitute it into the matrix, find the determinant of W using AD minus BC, then you will get this equation of the final answer of 3. Okay. The next step is to find U1 prime and U2 prime using the given equation. U1 prime equal to negative Y2 Rx over W, and U2 prime equal to Y1 Rx squared Rx over W. Substitute all the values, all the functions, and you will get the values of U1 prime and U2 prime. I just provide notes here that cosec theta is actually 1 over sine. So this one you can change to 1 over sine to solve the U1 prime. After getting U1 prime, U2 prime, again integrate the function to get U1 and U2. After getting the U2, substitute it to get YP. After getting YP, add YH and YP together to get the general solution of the non-homogeneous ODE. Okay, a summary for this lecture. So, in short, we have covered 2 methods to solve linear non-homogeneous second ODE, which are undetermined coefficient and variation of parameters. So for both methods, the general solution is the same that we have used previously in lecture 6 and 7. And the homogeneous solution, for general solution, it's a new formula that we have introduced in lecture 8, which is y equal to YH plus YP. We have to find YH using the method that we have covered in lecture 6 and 7. And for YP, we have to use undetermined coefficient or variation of parameters. So for solving non-homo solution, for undetermined coefficient involves guessing the YP based on the Rx. So if the Rx is a polynomial, then the YP is also polynomial, but we have to change the constant A, the values into unknown constant A, B, and C. Step to solve undetermined coefficient method is to guess YP, substitute YP into the ODE back, and compare it into the right-hand side to find the A, B, C values. After you get the unknown values, just substitute it to YP and find YH. For variation of parameters method, a specific equation for YP is already there. So we don't have to guess. This is a specified equation. YP equal to U1, Y1 plus U2, Y2. We have to find the first step to solve the ODE using this method is to find the Wronskian determinant of y1 and y2. From the Wronskian, we can find u1 prime and u2 prime, integrate it later to get u1 and u2. After getting u1 and u2, substitute back into yp here, substitute here, and you can find y by adding yp and yh together. So another reminder for undetermined coefficient method, the guessed yp must be modified if the terms in yp is equal to any of terms in yh. Modified means multiplying by x or x squared or x cubed. And then variation of parameters. The ODE, you have to check the ODE. The ODE must be in general form. If you forget to transform it to general form, then your answer will be incorrect. How to know if it's general form or not? See the numbers in front of y double prime. The y double prime should there shouldn't be any numbers inside in front of y double prime for ODE in general form. All right, that is all for lecture 8. Please ask Ken to submit your feedback. Thank you very much.